Hey there, and welcome. All around us, in the air we breathe and the water we drink, there are these incredible, invisible forces at work. They decide how a giant steel ship can float and how a tiny pedal can stop a car in its tracks. Today, we're going to make those forces visible. We're taking a deep dive into the world of fluid statics. So let's start with a little puzzle. What could your car's brakes and a massive container ship possibly have in common? I mean, one is all about stopping with incredible force, and the other is about, floating. They seem like total opposites, right? Well, by the end of this, you'll see how they're actually two sides of the same coin, ruled by the exact same physical laws.
But before we can crack that puzzle, we've got to get a handle on the most basic idea of all. We need to talk about pressure, and what exactly that means when we're dealing with fluids.
First things first, what even is a fluid? Well, it's not just liquids like water or juice. A fluid is basically any substance that can flow and change its shape to fit its container. And here's the key thing you got to remember. That definition includes gases. So the air all around us, that's a fluid too. Keep that idea in your back pocket because it's going to be a big deal later on.
In pressure, it's really just about force spread out over an area. Think of it like this. If I push on your shoulder with my whole flat palm, you'll feel it, but it's no big deal. But what if I take that exact same amount of pushing force and focus it all onto the tiny tip of one finger? Yeah, that's going to hurt. Same force, much smaller area, way more pressure. And we measure that pressure in a unit called the Pascal.
All right, with those basics down, let's meet our first genius, the brilliant Blaise Pascal. He came up with a principle so powerful, it literally lets you stop a 2-ton SUV with a simple push of your foot.
Pascal's principle is beautiful because it's so incredibly simple. What he figured out is this. If you have a fluid in a sealed container, like say a water bottle with a cap on tight, and you squeeze it anywhere, the pressure doesn't just stay where you squeezed. Nope, it instantly shoots out totally undiminished to every single part of the fluid and the walls of the container. It's shared equally, everywhere, all at once. And this is where we get clever. We can use that principle to do some amazing things. In a hydraulic system, you apply a small force to a small piston. That creates a certain amount of pressure in the fluid. Now, thanks to Pascal, that exact same pressure travels through the fluid and pushes on a much larger piston. But because that second piston has a way bigger area, the force it pushes out with is massively multiplied. It's a straight-up force multiplier.
And boom, we're right back at your car. This is precisely how your brakes work. Your foot puts a little force on the brake pedal, which pressurizes the brake fluid. That pressure then gets transmitted to the much larger pistons in your brake calipers, which then clamp down on your wheels with enough force to stop thousands of pounds of moving metal. You've just used Pascal's principle.
Okay, so that's how it works in a sealed system. But what about when a fluid isn't sealed up? Like in the ocean, a lake, or even just a glass of water on your desk. For that, we need to go a little deeper with our next thinker, Simon Stevin. Stevin's law describes something you've probably felt yourself. If you've ever dived down to the bottom of a deep swimming pool, you feel that pressure building in your ears, right? That's Stevin's law in action. The deeper you go, the more pressure you feel. And why? Well, it's because there's literally more weight of the water stacked on top of you pushing down. So pressure is low at the surface, and it gets higher and higher the deeper you go. And this law leads to this really cool, kind of weird visual magic trick called communicating vessels. If you take a bunch of containers, all different shapes and sizes, and connect them at the bottom, when you pour water in, it will settle at the exact same height in every single one. It looks strange, but it has to happen. Stevin's law demands it. For the pressure to be equal at any given depth across all the tubes, the height of the water above has to be identical. Okay, let's build on that. We've seen how pressure works inside a fluid. Now let's look at how that fluid pushes back on things that are put in it. It's time to talk about Archimedes and his legendary eureka moment in the bathtub.
Archimedes' principle is the absolute key to understanding why some things float and other things sink. It's simple. When you put an object into a fluid, it pushes some of that fluid out of the way, right? It displaces it. The principle says that the fluid pushes back with an upward force. We call it the buoyant force that is exactly equal to the weight of the fluid that got pushed aside. The fluid is literally fighting to get its space back. So it becomes a simple tug-of-war. You've got the object's own weight pulling it down, and you've got this buoyant force from the fluid pushing it up. If the object's weight is more than the buoyant force, it sinks. Game over. If they're perfectly matched, it'll just hover, suspended in the fluid. But, and here's the secret to our giant ship, if the buoyant force pushing up is stronger than the object's weight pulling down, it floats. A huge steel ship floats because its hollow shape displaces an enormous volume of water, creating a massive buoyant force that easily overcomes its own weight.
So we've looked at pressure in sealed containers, and we've looked at pressure under the water. For our last piece of the puzzle, let's zoom all the way out. Remember how we said air is a fluid? Let's apply these exact same principles to the biggest fluid system of them all, our planet's atmosphere.
I want you to just think about this for a second. Right now, wherever you are sitting at the bottom of a vast, deep ocean. It's an ocean of air, and just like an ocean of water, that entire column of air stretching miles above your head has weight. And all that weight is exerting pressure on you from every single direction. So how do we know this pressure is real if we can't see it or feel it? Well, a physicist named Evangelista Torricelli proved it with a totally brilliant experiment. He filled a long glass tube with mercury, a really heavy liquid, and flipped it upside down in a dish of more mercury. The column in the tube started to fall, but then it just stopped, suspended in the air. What was holding it up? It was the invisible weight of the atmosphere, pressing down on the mercury in the dish, perfectly balancing the weight of the column in the tube. He had just invented the barometer.
And he measured it. On average, at sea level, this atmospheric pressure is a whopping 101,325 pascals. Now that's just a number, but trust me, it's a huge amount of pressure that this ocean of air is constantly pushing on us with.
Which brings us to our final and maybe most incredible question. That amount of pressure is basically like having the weight of a small car spread out all over your body. So why aren't you crushed? Why don't you feel it? The answer is amazing. It's because the fluids inside your body, your blood, the water in your cells, are pushing outward with the exact same pressure. It creates a perfect balance. You, right now, are a living, breathing example of fluid statics in action, perfectly balanced against the invisible forces that shape our entire world.